Okay, recording is going on. All right. I welcome you everyone to this prepone session actually for week 5. So we are supposed to have our session on Saturday, but due to my inconveniences at my end, so we have preponed the session to Tuesday. Keep in mind that this preponement is just for 2 sessions only. That is the session on Tuesday, as I have said, the session which is supposed to be on 24th August, which was on Saturday, from 3 to 5 is preponed to today, that is Tuesday from 6 to 8. And the session on 31st, that is, so just like you have received the mail for the preponement of this session, similarly, the session on 31st August, that is on Saturday from 3 to 5 is postponed to 8 September Sunday from 3 to 5 p.m. Okay. So it's just for 2 sessions only. That is for the sessions on 24th and 31st. All other session, apart from just these 2 sessions, will be on the usual Saturdays from 3 to 5 p.m. I hope this is clear. I will post it in the discussion forum also, just for you to be clear. I repeat that similar to today, that is the preponement of 24th August session to today, that is from 6 to 8 p.m. on Tuesday. The session on 31st August, Saturday, which was supposed to be from 3 to 5, is postponed to 8 September, Sunday from 3 to 5 p.m. Okay. And the remaining session, the remaining whichever Saturdays we have, okay, we will meet in the usual time from 3 to 5 p.m. Okay. So this adjustment is just for 2 sessions only, and keep in mind it is not for all the sessions. Okay. So I hope this is clear. So I hope everyone is very clear on this. Anyway, you will also receive a separate emails just like what you did today in your through emails, and also it will be posted in the website as well. Okay, so with this, let's begin with our discussions on this week. So let's quickly recapitulate what we learned in the previous week, and then we will start off with this week's agenda. So in the previous week, that is on week 4, we looked into a very important aspect of heat transfer, which is basically heat generation in slabs and cylinders. Okay, so there, what we saw is we tried to understand how to use the Fourier's law whenever there is heat generation taking place inside the bodies. For instance, it could be a slab. In case of slabs, we use the Cartesian form of the heat diffusion equation. In case of cylinders, we moved into the cylindrical space, and there we use the cylindrical there we use the heat diffusion equation in cylindrical coordinate system. So we solve a couple of problems related to it. For instance, in the first problem, we were asked that there was a body where its face was insulated in one end, and in the other end, the temperature was prescribed. In that context, it was said that there was an uniform heat generation taking place inside the body, and we were asked to find the expression for the heat flux as a function of the spatial coordinate, keeping in mind that it's a 1D heat transfer problem. Okay. So we solved that by using what we have seen repeatedly, the heat diffusion equation, and came into the conclusion by using the necessary boundary condition that our heat flux is proportional to x. And this, as I said, is indeed the case, because when we have heat generation, you have derived that in your in your lecture classes, that your temperature profile is parabolic in nature, provided our heat transfer is one dimensional and heat generation is uniform throughout. In that context, we have seen that the temperature profile is parabolic, which means that the flux, which is nothing but the gradient of temperature, has to be linear in x. Okay, so this is something that we saw. In the second problem, this was much of an involved problem where we basically find out several things related to heat generation, where the temperature profile was now given to us, and we were asked to basically find out a lot of things. First, to sketch the temperature profile, then to evaluate the heat generation rate, then the fluxes, and finally, as a homework, I said to evaluate the heat transfer coefficient that is basically associated with these fluxes. So the important that is the important information that can be extracted from this problem is that although there was a uniform heat generation taking place inside the slab, and the temperature profile was parabolic, we saw that due to the difference in the values of the heat transfer coefficient, which we didn't know a priori, but we saw that the fluxes at these phases and these phases were not equal, which was contrary to one of the problems that we solved maybe in the first class, where we saw that if there is a uniform heat generation taking place inside a slab, okay, and then yeah, if there's a uniform heat generation taking place inside a slab, and then if the ambient fluid had the same temperature and the same heat transfer coefficient, then the temperature profile was symmetric about the mean line, that is at x equal to 0. However, in this case, what we saw is that since the fluxes at these phases and these phases were not equal, this means that it will be the case where the rate of heat dissipation from the body to the solid at the right phase and the rate of heat dissipation from the body to the solid at the left phase won't be the same. And this is attributed to the fact that the heat transfer coefficient uh, of these two phases are not the same. Okay, so this was basically the qualitative reason why the temperature profile is not symmetric. However, as a part of your homework, I said that I asked you to evaluate the heat transfer coefficient. So can you kindly just give me a hint? How do we now evaluate this heat transfer coefficient? Provided, what did we know? We know that the fluxes that came from these phases and these phases we have evaluated. So can you now tell me quickly how do we evaluate the heat transfer coefficient? Just a hint, and it will be a good recapitulation also. What do we need to use in order to evaluate the heat transfer coefficient here for these phases and these phases? Yes, can you give me a hint? Or at least did you, if you guys have evaluated it at your end, you can also tell me the answer, or else I'll just show you how did we evaluate the heat transfer coefficient. Yeah. So basically, it's very simple. So basically, we need to use the continuity of fluxes at the energies, which I have repeatedly said that, and of course, you have repeatedly seen that at the interfaces, for instance, if we are seeing at this interface, whatever the flux that is coming from this slab to this interface should be dissipated to the surrounding fluid, which means that I can write that at the right interface. Uh, so basically, what I can do is that I can write that at x equal to L, okay, what I can write? I can write that minus k of the block or the slab times dt by dx at x equal to L is basically equal to what? Can you tell me what this is equal to? Uh, I hope this is not that tough, right? So it is, we just need to write, so we are basically just balancing fluxes. So the flux that is coming out from the slab, okay, to the interface needs to be dissipated because we know that interfaces cannot store energy, at least in this context that we are currently studying, okay? So this means this should be equal to what? This should be equal to the convection flux, right? So the convection flux would be the heat transfer coefficient towards the right, okay, times the temperature at x equal to L minus T infinity. Okay, now everything is known to you, right? So this flux we have already evaluated because we know the temperature gradient. So you can evaluate this flux. In fact, we have evaluated that this flux is equal to what? So the flux at x equal to L is basically 5050. So this is nothing but just 5050. Okay, this is just 5050, and this we are supposed to find. Okay, and T at x equal to L is also something that we have evaluated in this problem. Okay, so what was T at x equal to L? So T at x equal to L is 69.8 degrees Celsius. Okay, so this was basically T at x equal to L was basically 69.8 minus T infinity, I think it's 20 degrees Celsius. Yes, T infinity was 20 degrees Celsius. So this is basically minus 20. Okay, which means from here you can very nicely evaluate the heat transfer coefficient HR as just this 5050 divided by 69.8 minus 20. Okay, just do this math at your own and you will get the heat transfer coefficient having the unit watt per meter square Kelvin. Okay, similarly, using the same principle, exactly the same principle, you need to apply this for x equal to minus L. Okay, and when you write this for x equal to minus L, this will basically be minus k dt by dx at x equal to minus L is equal to your heat transfer coefficient of the left times your temperature at x equal to minus L minus T infinity. Okay, and if you do this, just do the same principle as we did now, that you can easily evaluate your heat transfer coefficient HL for the left phase. Okay, just do this math, you will get some value with an unit watt per meter square Kelvin. Okay, so this was something that we saw, and I asked you to do this as a part of your homework, or you can do this at your end at any time. I hope you have at least tried to do it, or at least have evaluated it. This will obviously like help you in assist in thinking how to basically solve such kind of problems when you encounter these kind of problems, and yeah, it will of course try to do it whenever like you get a chance of like solving this kind of problem. Okay, anyways, we ended this problem by solving another important problem which involved heat generation in a cylindrical pipe having an inner radius r r1 and an outer radius r2, given the fact that the cylinder is insulated in its outer radius. Okay, so the idea was again this was related to heat generation, but this time it was in cylindrical coordinate system. So the idea was to solve the heat diffusion equation in cylindrical coordinate, as you can see from here, to get the temperature profile which we derive, and then using the boundary conditions we have derived the constants C1 and C2. The boundary conditions, as I repeat, was such that first was the no insulation boundary condition, which means that the flux at R equal to R2 is basically equal to 0. This is the physical manifestation of the fact that the cylinder is insulated from its surface. Also, they have said that in order to evaluate the second boundary condition, they said that this surface was now at a prescribed temperature Ts2. And from that, we evaluated the constants, which were evaluated the unknown constant, which were C1 and C2. And thereafter, once we evaluated the constant, thereafter they also ask us what is the heat removal rate. And for that, it is simple because we know that the cylinder, which for which we are solving the heat division equation, is being convectively cooled by a flowing fluid that is flowing through its annulus. Okay, and for that, they ask us that if the fluid is flowing through its annulus, okay, what is the heat removal rate that the fluid is basically extracting from the cylinder? And for that, it was very simple. We used the Fourier's law, and we applied this at the surface R equal to R, and this is precisely the rate of heat removal rate from the cylinder. And we were then asked to evaluate the heat transfer coefficient, for which what we did is we just did exactly what we did some time ago. We equated the conduction flux to the convection flux. Okay. Mm. This is something that we did in the last week. I stop here for some time. If you have any questions, related to whatever we did the last week, or or any other week, or if you have any questions regarding solving the assignments, regarding any problems related to the assignments, you can ask. I'll stop here for a couple of minutes, and then today we will start off with an even more interesting topic, which is known as heat transfer in extended surfaces, and we will see how this goes. But in the meantime, you can ask me if you have any doubts uh, related to anything, whether it may be regarding the last week's work or the assignment problems or things like that. Okay. All right. I'll stop here. If you have any questions, you can ask me, or you can. Sure. And if you have any questions in between, you can always feel free to interrupt me. You can just type in the chat box, or later on you can post it in the discussion forum, and I'll be happy to answer it. I'm still left to answer one question in the discussion forum. I saw that question, but I didn't find time like to look into what we did. I'll do that maybe by today, and I'll post it in the discussion forum. Okay. All right. If you have any questions, I can. So we'll wait for maybe 1 or 2 minutes more, and then we will start something which is known as heat transfer from extended surface. And the common name of these surfaces are known as fins. While I'll just check the recording. Yeah, I think it's going on well. Okay. All right, guys. If you don't have any questions, let's get started with today's today's agenda. That is basically understanding how heat transfer takes place from extended surfaces. So I'll begin. So I hope like you guys will answer some of the questions. Uh, so I'll begin by asking a question here, okay, and then I'll proceed with what needs to be done. So I hope like at least I think the assignment 5 are released, which is basically related to extended surfaces only. And I hope you got a chance to watch the lectures of, week 5, which is again related to extended surfaces. It starts off with understanding the heat diffusion equation that we write for an extended surface. We got so basically it starts off with the fact that you take a long surface, it's a long fin, then you derived what the temperature profile would look like. For instance, you take some so it's like you kind of solve the heat diffusion equation there, and you make a transformation telling that theta is basically theta minus tb, where tb is basically the base temperature of the fin that you guys have seen, and then you basically solve an equation which is something like this: d2x by dx2 minus I think m square theta basically equals to 0. This is something that you kind of solve subjected to the boundary conditions. Now, boundary conditions, let's say, so for instance, when I'm taking a fin, okay, this might be my base surface, and it is called the base surface because it remains at some temperature Tb, and this is the surface from which we are trying to extract the heat, such that the rate of heat transfer is enhanced. Okay, and then let's say we are attaching a fin here. Let's say my fin is cylindrical in nature, so my fin becomes something like this. Okay, and then what you do is these boundary condition, that is the boundary condition on the left, this always remains the same. We say that the temperature here, so remember the theta that you, so if you guys remember the theta that you took, the transformation variable is basically nothing but the temperature of the fin at any axial location minus the base temperature Tb, because this surface is at a base temperature which is basically known as Tb in this case. And theta is basically the temperature at any axial location of this fin minus the base temperature. So remember when we used when so basically when you guys solve the governing equation, which looks something like this: d2 theta by dx2 minus m square theta equals to 0, where your m, if you remember, can you tell me what was the value of m? M was something related to the physical properties and the dimension of the fin. Can you remember what is m? Yes. Can you quickly try to remember at least and tell me what is m? Uh, yes. Yes, exactly. You were right, Sanvi. You were right. It's p. So actually, what you wrote is actually m square. M is basically under root of ph by k ac. Okay. So it is basically the square root of that. Okay. So yes, exactly. Thank you, Sanvi, for the answer. Yeah. So what I was telling in that in order to solve this equation, this is basically a second order equation, which again I said that you require two boundary conditions as you guys have seen. So the left boundary condition, if you guys remember, this left boundary condition, so this always used to remain the same. Okay. So and this is nothing but theta, which, so can you tell me what was the left boundary condition? So can you tell me what is theta at x equal to 0, if you remember? This was just the base temperature theta b, right? Okay. So theta at x equal to 0 is nothing but the base temperature, which was theta b. Okay. And then the only difference that came into the picture was that the boundary condition that we used to write in the left, sorry, in the right surface. Okay. For instance, if I have a long fin, the very first case that you solved was for a long fin, which means that the length of the fin is so long with respect to its cross section. Okay. In that context, we use the different boundary conditions. The second case was that there is this boundary condition which is known as insulated tip boundary condition. For instance, instead of now in the first case, which we had a long fin, okay, the fin length was sufficiently long with respect to its dimension, while in the second case, that is the insulated tip boundary condition, the length of the fin is not that long, but this tip is basically insulated, which means that the flux from this tip, that is the flux at x equal to L, is basically equal to 0. Okay. So so this is something that you guys saw. So the only, so what I want to convey from this point is that depending on the boundary conditions on the right hand side, end of the fin, we got different expression for number one for the temperature profile, that was theta, okay, and second the rate of heat transfer, that was taking place from the fin. For instance, okay, if we have an insulated tip, so for instance, if we have an insulated tip condition, then the rate of heat transfer was, so if I correctly remember, the rate of heat transfer, so correct me if I wrong. For instance, if I have an insulated tip, that is Q dot insulated, then the rate of heat transfer was under root of PH K AC theta B 10 hyperbolic ml. It was something like this. Correct me if I am wrong, but I think it was something like this. On the other hand, let's say if we have a long fin, then the rate of heat transfer was basically equal to under root of PH K AC theta B. So as you can see, depending on the boundary conditions on the right hand side, okay, depending on the boundary conditions on the right hand side, your all other things, whether you are now using a long fin, an insulated tip fin, or a or see, I didn't say the other two boundary conditions. The other two boundary conditions were that there was a prescribed temperature on this fin surface, and the fourth boundary condition was that there was a convective heat flux that is being released from this surface. So there were four boundary conditions basically, I think, and that is something that we have seen in the last class. Okay, so the idea is that depending on these four boundary conditions taking place on the right hand side of the fin, we have defined expressions for the rate of heat transfer, okay, and two more, that is basically the fin parameters, the fin effectiveness and the fin efficiency. But we will see all these things, but the bottom line is that the idea of solving the heat diffusion equation remain the same irrespective of whichever boundary condition you choose at its right phase, but its expressions obviously differs because now obviously the boundary conditions will be different for the different four cases. The four cases where I reiterate, number one, the long fin case, that was the most simplest case that you saw, right? And second, the insulated tip case, which means that there won't be any flux coming out from this interface. The third case was that this surface is being convectively cooled, which means that the flux that is coming out from here is equal to the convection flux. That is something again that we saw. And the fourth boundary condition is that instead of it being convectively cooled, okay, they have prescribed the temperature here, that on this phase the temperature is known. For instance, if on this phase, if my theta is basically theta B, then they have said that on this phase, let's say my theta is basically some theta R, which is known a priori. Okay. As I said, depending on this, the boundary conditions of the fin varied. And the expression for the rate of heat transfer, the fin effectiveness, the fin efficiency also varied. Okay. But the bottom line is that, so the idea is that irrespective of whatever boundary condition you use, we just need to solve the heat diffusion equation, okay, which is basically this equation is not, so you can see, right, this equation is universal, it does not, obviously so if you just apply, so this equation is valid at each and every point of the fin, okay, it's just the boundary condition that differs. All right, so quickly I would just like to I would just like to reiterate two more things and then we will start solving the problems. Can you now tell me, based on this, we define two important fin characteristics. One, there is something which is known as fin effectiveness. Can you quickly tell me what is fin effectiveness? This is a direct question of your assignment. You were asked to basically answer what is fin effectiveness. Can you tell me what is fin effectiveness? Yes. So try to understand uh, why do we basically define effectiveness, okay? So when we define effectiveness, we are kind of defining it to a scenario when that particular thing is not there. That's the hint of the answer to this fin effectiveness. So now can you tell me what is fin effectiveness? Yes. You can give it a try. I mean, you can give it a try, and it's not that there will be a correct answer or a wrong answer, but okay, so I'll tell you what, yes, heat transfer ratio with fins, yes, exactly. So you are right. So basically what Sanvi says is that fin effectiveness is rate of heat transfer Q dot when there is a fin, so we'll write it as Q fin, and rate of heat transfer when there is without fin. Okay, so this I'll write it as without fin. Okay. Similarly, there is one more thing that is known as the fin efficiency. I hope you know these things. I mean, meaning that I think you know what's the expression of fin efficiency. So while effectiveness says that what will be the rate of heat transfer, okay, that will take place from a fin to the rate of heat transfer when there is without fin. Efficiency says that the so efficiency, fin efficiency, it is the ratio of rate of heat transfer with fin to the rate of heat transfer to the maximum rate of heat transfer from that particular fin. Okay, so these are the two performance parameters that we define in case of fins. I repeat, the fin effectiveness is basically the rate of heat transfer from the fin to the rate of heat transfer if there was no fin, and fin efficiency is the rate of heat transfer that would take place from the fin to the maximum rate of heat transfer that would take place from the fin. Okay, now try to understand that not always okay, not always adding a fin will enhance the heat transfer. For instance, why I tell this fact is that, see, what we are trying to do is, see, consider a scenario when there was no fin. Okay, if there was no fin, this entire surface would have just convectively released the heat to its surrounding. Now what we are trying to do is we are trying to add an additional, let's say, a material. We say that this material bears, so this material is very thin, that is the perimeter to the perimeter to surface area is very less, okay, such that this material would enhance the rate of heat transfer, but the bottom line is that this material would also add a additional conduction resistance to its path, right? So it's not that readily you just stuck a material and that would just decrease your rate of heat transfer, because while this material is trying to like release the heat to its its surrounding, it itself will pose a conduction resistance to its path. So the objective is that we try to minimize this additional conduction resistance of the fin such that this material will enhance the rate of heat transfer with respect to the case when there was not this fin that was present. Meaning that in very simple and in very like layman words, we can say that in order in order to be for the fin to be effective, okay, for the fin to be effective, as it says, the effectiveness of this fin should be always greater than 1. This is the condition which says, so if effectiveness of a fin is always greater than 1, this means that if you go on and add fins, it will always increase the rate of heat transfer. Okay, so based on these theories, okay, that we see, we will solve our first problem. Okay, it's not this problem. So this is our first problem that we'll solve. The earlier problem will come in a later stage. So it says that establish a relationship between fin effectiveness and fin efficiency. Okay, and while doing so, we will look into like some important conclusions that I have just said. So for instance, as you have correctly pointed out, that your fin effectiveness is basically rate of heat transfer with fin to the rate of heat transfer without fin. Now you need to tell me that if I now have a base surface, okay, and this base surface has got an area AB, which is basically the area of the base surface, okay, right? I'll for the time being, I will just neglect this AB. I mean, we'll see this, but for the time being, just make clear. Just 1 second. Yeah. So what I was trying to say is that now let's say we have a base surface, basically this. So this surface is basically known as the base surface. Okay. And this surface, so I'll tell that this base surface have an area AB, which means that this entire surface has got an area AB. Okay. Let's consider the area of the base surface to be AB. So in this context, if I now attach a fin, okay, if I now attach a fin, and for the time being, let's say it's a long fin to simplify our calculation. So this is the fin, okay, and the cross-sectional area of this fin will denote it as AC. So AC is basically my cross-sectional area of the fin. Okay, in this context, can you tell me what will be, so Q dot fin, we'll just keep it as Q dot fin. Can you tell me in this context, what will be the rate of heat transfer that will take place from this surface if there was no fin. Okay, I'll give you one more information. The heat transfer coefficient is H, and others I think you guys know. This base temperature, we'll consider it as theta B. Okay, so can you tell me based on this, what is this value? Rate of heat transfer without fin. Can you tell me in terms of this H, theta B, and this area? Can you tell me? So the objective is to relate the fin effectiveness and fin efficiency and see how these two like, so we'll try to establish a relationship between the fin effectiveness and fin efficiency. So can you now tell me what will be the rate of heat transfer without fin? We have not, yes, H A B delta T. Delta T means theta B. That's what I think you meant. Yes, exactly. So the rate of heat transfer without fin, as you have rightly like pointed out, is the heat transfer coefficient. That is basically the Newton's law of cooling, right? That's what we have seen multiple times. So it's going to be H times area of the base times theta B. Theta B is basically the base temperature. We will denote it as, so the delta T will denote it as theta base. Okay. So this is something that we get from the definition of fin effectiveness. All right. Now, can you tell me what is the efficiency? So efficiency, as I said, is nothing but the rate of heat transfer from the fin to the maximum rate of heat transfer from the fin. Okay. Now, here is my question. We will keep the numerator as it is. It is just going to be q dot fin. That is typically because we have q dot fin here also and we have q dot fin here also. So we'll not will not use, so we'll not substitute the value there because it will just be cancel out, or like when you are trying to establish a relation, this factor won't be there because it bears its nature in two forms. Okay. But now can you tell me in what condition the fin, or my question is in what condition the like fin would dissipate its maximum heat? Okay. Can you tell me what is the condition under which there will be maximum rate of heat transfer from the fin? Can you think of it? You have correctly pointed out that the rate of heat transfer without the fin is HAB theta B, which is basically the heat transfer coefficient times the area of this base multiplied by the temperature difference of the base and the ambient. For instance, this theta B, okay, this theta B is going to be TB minus T infinity. By the way, I kind of slightly made a mistake here. I mean, that's from my end. So theta was not this thing. Theta was basically the temperature of the fin, okay, at any point minus the ambient temperature. I wrongly wrote it as theta B. This will be T infinity. Okay. Sorry for that. But anyways, can you now tell me under what condition the fin would dissipate maximum temperature? Can you tell me? I mean, can you give it a try? Yet, okay. So what Sanvi says is that at x equal to 0, t equal to theta b. That is true. That is true, Sanvi, that at x equal to 0, x equal to 0, the fin temperature would be theta b. But my question is, so that is, so what you said, that is for a practical fin, right? See, for a practical fin, the temperature here would be theta b, okay? And when you move in this direction, the temperature would ideally decrease. But in an ideal scenario, for the fin to dissipate its maximum heat, okay, the entire fin has to be at the base temperature. What I mean is that when you move from here to here, if my fin temperature is equal to the base temperature, in that scenario, your fin can dissipate the maximum heat. And this is kind of a limit. Just like the Carnot cycle is a Carnot efficiency is a limit, this Qmax maximum is a limit to the maximum heat transfer that the fin can dissipate. Okay, so I'll write it here. So Qmax is, so this is basically the maximum heat the fin can dissipate and it is possible when the entire fin is at the base temperature theta b, meaning that I hope you have understood this. This means that whether I am in this cross section or in this cross section or in this cross section, throughout this entire cross section, okay, throughout this entire cross section, the fin temperature is just the same and it is equal to the base temperature. The physical insight or the physical meaning of this fact is that the conduction resistances within the fin is negligible. In that context, the entire surface of the fin would be equal to the base temperature theta b, and the only way the fin would dissipate heat is now by convection to its ambient. Okay. For example, if I'm in this if I am, let's say, in this cross section, my temperature would always be equal to theta b, and this would basically dissipate heat now to its ambient. Okay, and the mode of heat transfer is convection. In this scenario, the fin can dissipate the maximum heat. Is it so? Are you clear now? In what scenario the fin can dissipate maximum heat, and thus the definition of fin efficiency? Can you give it with an yes or a no? Or like, do I need to explain it again? I mean, I'll be happy to do that. So, okay, so did you understand the scenario? When can the fin dissipate the maximum heat from its body? Okay, yeah, sure. Thank you very much. Which means now, okay, so now can you tell me what will be this expression of Q max fin? So I have said the scenario when can Qmax fin occur. That is when the entire fin is at the base temperature. Okay. Now what will be this Qmax fin? So that also I have like hinted. So since now the entire fin is at the base temperature, the only way this fin can dissipate heat is by convection, right? So this would be the heat transfer coefficient times, I will define another parameter which is known as AF, which is basically the area of the fin. So this would be the heat transfer coefficient times the area of the fin times theta b. So is this clear? So this is basically the maximum heat that the fin can dissipate. That is obvious, right? Because the only way the fin can dissipate it to its ambient is by convection, right? Because the entire fin has got now the same base temperature, which means by conduction it won't dissipate heat, because we have now considered the fact that there is very negligible conduction resistances, which means that the only way this heat could go out now from the fin is by convection to its ambient. Okay, and what is the heat transfer that takes place due to convection? It is the heat transfer coefficient times the area. Now the area becomes the critical, because you need to consider the area of the fin. Now the area of the fin will encompass this surface area plus this cross sectional area. Okay, because these are the areas through which it will dissipate heat to the surrounding. Okay, and that's why I have written is AF. You can pinpointedly calculate AF depending on the geometry of the fin. And of course, this is theta b, because I have now said that the entire surface of the fin is at the base temperature, which means that the temperature difference that the fin would see when it dissipates heat heat through convection is Tb minus T infinity, and that's why we have written it as theta b, which is basically this what I was talking about. Okay, so this is the definition of your fin efficiency. These two parameters are very, very important, and frequently, you will see when you will see the usefulness of these two parameters. Okay, now the idea is to essentially relate this fin effectiveness and fin efficiency, and what we will now do is we will try to calculate, okay, from the definition of efficiency we will try to calculate q dot fin. So q dot fin becomes, so from 2, okay, so from 2, your q dot fin, this becomes the efficiency multiplied by q max, multiplied by this term q max from the fin, and this we have calculated as eta times h area of the fin times theta b. And what now we will do is we will substitute this q dot fin into this definition of effectiveness, because we have q dot fin here. Okay, so I hope the drill is clear. So what we will do is we'll substitute this, substitute in 1. So what was 1? Our 1 was fin effectiveness was q dot fin, okay, divided by the rate of heat transfer when there was no fin, which basically was h a b theta b. And now we will substitute the value of q dot fin from the definition of effectiveness, which becomes now effectiveness times h a f theta b by h a b theta b. Okay, some parameters would cancel out, your theta b and theta b would cancel out, h and h would cancel out. Okay, and then your effectiveness becomes Your effectiveness is basically your efficiency into area of the fin by area of the base. Okay, this is typically the relationship between your fin effectiveness and fin efficiency. I hope you are clear with this one. Okay. Right. All right. This is what the question has asked us to do. We'll do one more. We'll do one more thing. Okay. We'll do one more thing, that we will see the condition which, we'll derive the condition under which, okay, the use of fin is essential. Okay, and for that we will use the definition of fin effectiveness. So remember, what we said is that your fin effectiveness is basically q dot fin by HAB theta b. Okay, actually I think I made a mistake here. See, I think I made a mistake. Can you tell me where did I made a mistake in effectiveness? So I made a mistake in effectiveness. Okay. Can you tell me where did I made a mistake here? I made a mistake here in defining something. Can you suggest where did I made a mistake? So I'll tell you I made a mistake in efficiency. There is something that is wrong in efficiency. See, I will tell you. See, when we were defining efficiency, I said that it is the rate of heat. I said, in fact, you also said that it's the rate of heat transfer from the fin to the rate of heat transfer without fin. Okay. And then when I wrote q dot without, I wrote this area as theta b. But this is wrong, right? Because the fin is responsible only for dissipating heat through this area. The rest it will anyway dissipate to its surrounding, right? Which means instead of this being theta b, this should be AC. Sorry, instead of it being AB, it should be AC. Are you clear? Like why it is AC and not AB? Uh, is it an yes or a no? Can you tell me? Or I need to explain it again. See, I'll tell you why it's not AB and it's AC. Because what we are now trying to do is we are trying to compare what would be the rate of heat transfer if there was a fin from this area to the rate of heat transfer if there was no fin from this area. Okay, it's like you need to compare apples and apples, right? Because the remaining area, which is basically this will anyway this will anyway dissipate heat to its ambient, right? Which means that if we are comparing, we need to compare it. So we need to compare it to a standard like point, right? Which means that if I am comparing the rate of heat transfer using a fin, uh, and I am comparing that if there is no fin, then I must calculate this area and not the area that is being exposed earlier, because that area, it's like वो area तो पहले से ही था, so that will anyway dissipate heat to its ambient. So are you clear why this is AC and not AB? Uh, or you have some arguments on it. You have a different argument on it. Can you tell me? I mean, right? So it has to be AC and not AB. Just correct me, like if you have any other point on this. So it should not be AB, but it should be AC. That's the thing. Okay, that's the mistake I was making. Anyways, so this would be AB. This would be sorry. This would be AC, and then this would be AC. Okay, and then this would be AC. So this was the mistake I was making. So your effectiveness is essentially efficiency times the area of the fin to the cross-sectional area, AC. Okay. Anyways, and of course this has to be also AC. All right. So, anyways, just let me know like if you have any doubts on this, and I'll be happy to explain it again. If not, let's understand it. So the idea is that we are trying to derive a relation under which the use of fin is justified. Okay. For that, we will stick to the definition of effectiveness, that is the fin effectiveness. Now, can you tell me what is this fin effectiveness? Let's say I have so what is this fin effectiveness? Let's say I have a long fin. So can you tell me what is this q dot fin? So this denominator is h ac theta b. That is fine. This does not change irrespective of the nature of boundary conditions of the fins that we have. But can you not tell me what is q dot fin if I have uh, a long fin basically? If I use the long fin boundary condition, what is q dot fin? If you remember. Yes. So correct me if I'm wrong, q dot fin for a long fin is under root of phkac theta b. So did I write it correctly? If you remember, is it correct? So I hope I'm correct, right? That is, if you evaluate the expression of q dot for a long fin, it just comes out to be under the phkac theta b. Now let's look into the following. Okay, so this theta b and theta b would just get cancelled out, which means your effectiveness essentially comes out to be, if you simplify this, okay, it basically comes out to be under root of what? Under root of, so your kac will come down, so it is under root of pk by h times ac. Okay, so this is your effectiveness. So this is your effectiveness for a long fin. Okay, now can you tell me what is the condition that is imposed on this? Okay, for the use of fin to be justified. Okay, that means I'm asking that what should be the value of effectiveness such that I want to justify the use of fin, or in other words, the use of fin enhances the heat transfer and not the other way around. What should be this effectiveness? Okay, such that the use of a fin is justified. Can you tell me? So this should be greater than some value, or this should be less than some value, or this should be equal to some value. Can you tell me on that? And can you shed some light on that? Yes. Or in other words, I'll ask you like I'll ask you in a most simplified way. What should be this effectiveness of the fin? So will this yes, greater than one? Exactly. Yeah, exactly. It should be greater than one. So this is simple. That is simply because the definition of effectiveness is what? It is the rate of heat transfer with fin to the rate of heat transfer without fin. Which means if you now tell me that use a fin and increase the rate of heat transfer, this means that this q dot fin has to be greater than this q dot without fin, right? This means the use of fin is justified, as you have rightly pointed out. So the use of fin is justified if my fin effectiveness is greater than one, as you have rightly said, which means that under root of pk by hac is greater than one, which means that, so yeah, you can write it like this, or you can write it in this manner, that under root of hac by pk to be less than 1. So this is the condition which is essential for the effectiveness to be greater than 1. Okay, if you have a close look, you will have a assignment question very similar to this exercise that we did. All right, so this was the second part of this question which I want to bring into the attention. I ask you again, I hope you have understood why you have used this AC and not AB. Are you clear on this? Like, can you kindly give it an yes or a no? That, because I was making a mistake, right? So it's like, so did you understand why this is AC and not AB? Because AC is C. What is AC? It's basically this cross section, okay, where the fin is attached. And AB is the area of the entire base surface. Okay, I'll repeat it again. It's not AB. That is typically because, see, we are trying to compare the rate of heat transfer from an area when there was that fin with respect to the same area when there was no fin. Okay, so the area always needs to be the same. Okay, if we are using AC in trying to calculate the rate of heat transfer from the fin, then we should use the same AC in trying to calculate the rate of heat transfer when there was no fin. And that is typically the reason why this area is AC and not AB. The remaining area, see, what is the remaining area? If AC is already accounted, the remaining area is the base area minus AC. This remaining area will anyway dissipate heat to its surrounding by convection. So we cannot count that area into the picture. We always need to count that particular area on which we are attaching the fin. And in the second scenario, we are removing the fin and then trying to calculate the rate of heat transfer from that area. Are you like clear on this now? Can you give it an yes or a no? Yes. Yes. Thank you. Thank you. Yeah. Okay. All right. Okay, so this was the first question that we solved. It was rather an easy question, but it was very insightful. And you will see multiple assignment questions related to the exercise that we did now. Uh, all right. Okay, so we'll solve another problem, basically this. But before this, I want you to read this problem. In the meantime, I'll just fill my cup with a glass of water and I'll come back in 2 minutes. Okay. I want you to read this problem and then we will think of strategies to basically solve it. Okay. I'll come in 2 minutes. I'll just fill my mug with a glass of water and I'll come. All right, guys. Sorry for the interruption. So now we will see the second question. I hope you guys have read it. So let's try to understand what it says. So it says that a long circular aluminum rod is attached to one end of a heated wall and transfers heat by convection to a cold fluid. Okay, that's fine. This means from the problem, it hints that the aluminum rod serves as a fin. Okay. Now what it said is that if the diameter of the rod is triple, by how much would the rate of heat removal change? In the second case, that if a copper rod of the same diameter is used in place of aluminum, by how much would the rate of heat removal change? Okay. So the question seems so the question seems doesn't so from the question it seems that we have to use the concept of the fins. Okay. And from the question, can you tell me that which of the four boundary conditions that we first saw and you saw in this week's lecture series as well, that which of the four conditions, that is the long tip, the insulated tip boundary condition, the convection, the prescribed convection from the tip, and the prescribed temperature, out of these four, which one should be used to solve this problem? First of all, you need to appreciate that this is a fin problem, typically because it says that an aluminum rod is attached to one end of a heated wall, which means so it's kind of like this, that there is this heated wall. Okay. And then you are attaching an aluminum rod of some prescribed diameter. Sorry. Kind of basically attaching an aluminum rod. Okay. All right. And then this wall is heated. This wall is basically heated. Okay. And this means that the rod is now trying to increase the rate of heat transfer. And that's why it serves the purpose of a fin. Okay. The question is that if this is the case, and it is saying that it transfers heat by convection to a cold fluid, that is, it have a cold fluid here, which may be at temperature T infinity and a heat transfer coefficient H infinity. And it says that it is transferring heat to this cold fluid by convection. Okay. So under this case, which boundary condition from this problem should we use? I mean, we should use, because ultimately we need to determine what is the rate of heat transfer, and the rate of heat transfer depends on the right boundary conditions that we use. Okay. For instance, for a long fin, the expression of rate of heat transfer is different. For like insulated tip boundary condition, the expression is of course different. So which boundary condition do you think we should use in this problem? Is it an insulated tip or it's a long fin, or like it's convectively cooled, or I mean that prescribed convection from the tip, okay, or like a prescribed temperature at the tip. Which one should you think we should use here? So you should read the question for that. Like, what do you think? See, in the first place, it's already given that a long circular aluminum rod is attached to at one end to a heated wall. Okay, this means it already says that this the length of, so from the problem only it says that the length of the rod is very much long, which means that we will be like it will be okay for us if we use the long fin assumption. Okay, so I hope you are clear. So it just comes from the question only. The question says that the length of the rod so the question says that the rod is, one second. Yeah, so the question says that the rod is long enough, which means that we can now use the long fin assumptions. In that context, so so the idea is using the long fin, long fin like formulation. In that context, can you tell me what is the rate of heat transfer now? What is Q dot from the fin? See, because what they are asking us to compare, if the diameter is tripled, how much would the rate of heat removal change? So for that, at least we must first calculate what is the rate of heat transfer, and then we will see how the rate of heat transfer shows its dependence on the diameter. Okay. So can you tell me for a long fin, what is the rate of heat transfer? We just now saw it in the previous problem. What is Q dot F for a long fin? Yes, can you tell me? So the long fin is the easiest one, right? I mean, it's not that difficult. So Q dot F for a long fin, as we have seen, is nothing but under root of PH K AC theta B. Okay. So I think this is something that you guys have seen. I mean, at least you have derived this. So can you give it an yes or a no? Did you derive this expression or not in your theory? At least I didn't see the theory classes like from end to begin. Yeah. Okay. Thank you. Yeah. So I think you have derived this right in your theory classes. Basically, see, it's basically very simple. What you need to do is you need to solve this. Okay. You need to solve this for theta. Use the boundary condition for long fin, and using that you will get theta as a function of x, right? Now, in order to determine the rate of heat transfer, what you need to do is you just need to apply Fourier's law at this point. Okay, which means that if you just need, so Q dot is nothing but minus K times d theta by dx into AC. So once you calculate theta, just use this and just substitute theta here, and you will get this expression. This is the idea behind getting this expression of under the PHKAC theta B. Okay, I hope you have derived that. So I mean, I think you have at least like gone through the steps involved in its derivation. But on a broader perspective, that's the idea how this is derived. Okay. Anyways, so now let's see where from in which of these terms in this expression the effect of diameter is seen. Okay. So this means I can write it as Q dot fin. So what would be the perimeter? Can you tell me what is the perimeter of this fin? See, the heat transfer coefficient won't be a problem because heat transfer coefficient does not contain diameter. The perimeter contains diameter, right? Because if I write the perimeter, yeah, it's pi times d, exactly right. So your perimeter is basically pi times d, okay? Thermal conductivity is it's not dependent on diameter, right? So this would be just K and AC. So AC is now, it will, so as you say, the perimeter is pi times d and your AC would be pi by 4 times d square, right? And then this would be just theta b, which means I can now write it as what? I can now write it as Q dot F. If I just simplify, I can write it as, so what can I write? It's pi by 4. So what I can do is, see, this is, there is this pi and there is this pi. It will be pi square. So I'll take this pi square out of the square root, for which it becomes pi, and 4 would become 2. So it's pi by 2. This I will keep it like this, h times k. Okay. And then this would be d to the power. So there is this d square and there is this 1d. Okay. So this is d cube that is basically being taking place here. And when it comes of the square root, I think it would be d to the power 3 by 2. Please correct me if I'm making mistake in the algebra, but I hope it is fine. And then this would be theta b. Okay, so this is correct, right? So this means that for this circular fin, your rate of heat transfer, considering the fact that we are using the long fin formula, boils down to the fact that your q dot f is pi by 2 times square root of hk into d to the power 3 by 2 into theta b, which means that your rate of heat transfer for a circular fin, considering the fact that it's a long fin assumption, is proportional to d to the power 3 by 2. Okay, so now we will look into this. Now what basically we'll do is we will see what happens if the diameter gets triple. Okay, so they're asking us to compare the rate of heat transfer if this d increases from d to 3d. Okay, and for that, let's say my heat, so I know the dependence now, so now it becomes easier because I know that my rate of heat transfer is proportional to d to the power 1.5, which means I can now write it that, let's say my rate of heat transfer in the first case when a diameter was d was, let's say I'll write it as qdf, and in the second case, my rate of heat transfer if my diameter becomes 3d, I'll write it as q3df, and then this would be equal to what? This would be equal to, in the first case it would be d maybe, and in the second case it would be what, 3d. Okay, and then it would be to the power 3 by 2. Okay, so I'll put the, like, so this d and this d would basically cancel. Okay, and this would basically become what? This would be qd. I'll write the larger one in the numerator and the smaller one in the denominator, and this would basically become 3 power 3 by 2. Okay, this is, so 3 power 3 by 2, or this basically can be written as 3 power 1.5, and if you evaluate this in your calculator, this will roughly come out to be around 5.2 if I'm not wrong. Okay, which means that if your diameter increases from d to 3d, your rate of heat transfer, basically this is q dot 3df, is basically equal to 5.2 times your rate of heat transfer when your diameter was just d. Okay, this is basically the answer. So can you tell me how much percentage increment has taken place if your diameter increases from d to 3d? The factor is 5.2, of course. So if you estimate this, you will get an increment of around roughly 400%. Okay, 400 or 420% maybe. So you'll get a roughly around 420% increment. Okay, so I hope this is clear. Okay, so I hope this is clear, right? This was not that tough. Okay, so the idea is that, so what we did, the idea is that we first established the expression for the rate of heat transfer in case of a long fin, and then what we did is we tried to understand how this rate of heat transfer shows its dependence, or how, or it's like how the diameter shows its dependence on the rate of heat transfer. We established that the rate of heat transfer, keep in mind, for a circular fin, okay, and using the insulated tip boundary condition, boils down to the fact that q dot f is proportional to d to the power 3 by 2. And then use basically the fraction rule to like establish the fact that when your d increases from d to 3d, your rate of heat transfer will be, in case where your diameter was 3d, is equal to 5.2 times your rate of heat transfer when your diameter was just d. Okay, and then if you evaluate the percentage, you will see that you will get an increment of around 420% increment. Okay, all right, I hope this is fine. So now, can you tell me what will be the answer for the second part? So we already evaluated this. The second part, it says that if now I have a copper rod of the same diameter is used in the place of an aluminum rod, by how much the rate of heat removal would change? So now can you tell me what is the dependence that the rate of heat transfer shows on? So first of all, what will change if I transition myself from an aluminum rod to a copper rod? Can you tell me in this expression what will basically change if I transition myself from a aluminum rod to a copper rod? Which term would basically change? Copper rod has, yeah, exactly. You have pointed it correctly. Exactly. This means what you are saying is that the thermal conductivity will change. All other terms, for instance, this heat transfer coefficient, this diameter, this theta b, would exactly be the same. Okay. And yes, you have correctly pointed out that copper has a greater thermal conductivity uh, than aluminium. I think that is what you said, right? Yes, copper has a greater thermal conductivity. Yes, exactly. Now this means that if I now want, so can you tell me what is now the dependence? Yes, you have pointed out that copper has a greater thermal conductivity, but can you tell me what is the dependence on this QF? So just like diameter is so Q dot F is proportional to 3 by 2 power of its diameter. What is this proportionality if we are considering this K? It is half, right? So Q dot F is proportional to K to the power half, right? This is something that we need to do because all other things are just the same. I hope you are clear on this. So Q dot F is proportional to K to the power half for the same diameter. This means that if I now want to write it for copper, Q dot F by Q dot aluminium, it just become K of copper by K of aluminium to the power half, and then it just so. Can you tell me what is so the thermal conductivity of copper is roughly around 400 watt per meter Kelvin, while the thermal conductivity of aluminium is roughly around 240 watt per meter Kelvin. Okay, so this becomes 400 by 240 to the power half, and if you calculate this, this will be around 1.29, which means that the rate of heat transfer for copper is 1.29 times the rate of heat transfer in case of aluminium, provided I have the same diameter. Okay. And then if you want to calculate the percentage increment, this this would be roughly around 29%. So this means that if you are using a copper rod, this means that if you are using a copper rod in place of an aluminum rod, you will get your rate of heat increment for the same diameter, of course, you will get your heat increment to be 29%. But keep in mind that you are doing this exercise for a circular, for a circular fin, using the fact that you are considering the length of the fin to be long enough. Okay, and in that context only this expression that you wrote here, this expression that we saw here is valid. Okay. But still, I'll ask you a question here. This is of practical like significant. But still, in most of the like fin applications, for instance, if you see a bike engine, uh, the fin that you see in a bike engine or a car engine, okay, the fin is basically made of aluminum and not copper. Can you tell me why is that? Despite the fact that copper has a higher thermal conductivity than aluminum, can you tell me like why is that? Why is that the scenario? So generally, like if you see the fins in an automobile, it is generally made of aluminum and not copper. Yes, exactly. That's lightweight. Yeah, you have correctly pointed out lightweight, cheap. I don't think so. I don't know what is the cost wise like difference between aluminum and copper. But yes, aluminum is lightweight. And one more advantage that yes, I think aluminum is more cheap than copper. Okay, I'm not sure, but I think aluminum is, of course, it has to be cheap than copper because copper is expensive, right? Copper wire and aluminum wire is much cheaper than a copper wire. So yeah, cheap is also one thing, and the most important factor, apart from it being cheap, is the lightweight. So aluminum possesses a ease of machining than copper because of the fact that it is lightweight and it is cheap, and that's why even if like copper has a greater thermal conductivity, which is maybe twice that of aluminum, around twice that of aluminum, but still, you know, we prefer to use generally aluminum fins instead of copper fins. Okay. Anyways, good. Uh, I thank again for answering the questions. This in a way kind of like makes the section interactive. But yeah, this is the question. So I hope you have got what we need to do from this question. So this is what we need to do. So we have solved this question. So I think we have some time left. So we will begin, okay, although I'll not solve the numerical because this is something new to you, maybe, but I will give you an hint. So this is, so did you learn something in something known as overall service efficiency in your, in your, like lecture series? Did you learn this? So did you see this term in your lecture series? If not, like I will give you a flavor of how these things work, how these things work. I will not solve. So I was planning of solving a numerical associated with this. Maybe if you get time, we will do it in the next class. But at least for now and for today, I will give you an idea of what do we mean by overhead efficiency. Okay, because this is of great practical like importance. So all other problems on the fins, that is the problem that you have in your assignment and the theory problem, you are now in a good position of solving them. You can just go through it and you can easily solve them now. However, I wish to give you an additional information on something which is known as overall surface efficiency. Did you learn about this in the theory classes? If so, if you have learned, then I will not like spend time on like explaining what exactly is. So, did you see this? Can you just give it with an yes or a no? It's okay. I mean, I hope it's okay. We will just go through it once again. It's not that it's not. So if so, in case no, sir, I have not attended. Okay, that's okay. Yeah, that's okay. That's fine. That is completely fine. I mean, I think yeah, I think like this topic was not covered in the lecture classes, but it's okay. Uh, I mean, that's not a big deal. So we'll stop here maybe for 1 or 2 minutes, and then I'll give you the idea what do we actually mean by overall surface efficiency of a fin. See, by now, what we have seen is that we have just picked one fin, that is one, let's say, set of, that is just one particular fin, and we have defined something which is known as efficiency of a fin and effectiveness of a fin. But in reality, or in most of the practical applications, for instance, in bike engines or in car engines, or let's say in transformers, so in big transformers, they also use fins to cool it. So in all those cases, they do not use just one fin, right? And in all the practical application itself, they will not use one fin. Instead, they will use multiple fin stacked together. Okay, and in that scenario, in all these practical applications where they use multiple fins stacked together, just like this, or just like basically this. Okay, we define something which is known as overall surface efficiency instead of defining just the efficiency of a single fin like this. So it becomes easier and it becomes customary to use something which is known as overall efficiency instead of just defining the efficiency of just one fin. And I will show you how this overall efficiency is being calculated. Okay, but before that, like I'll stop here for 1 or 2 minutes. If you have any questions, you can ask, or else I will just show you how to basically what is this overall efficiency and how to basically calculate this overall efficiency. And then like we'll not extend today's class because it being a preponed class, like we'll not extend it too much time. We'll finish it once we are done with this. Okay. All right. So if you don't have any questions, so we will basically see what we mean by this overall surface efficiency. Okay, so as I was telling that instead of just defining efficiency for a single fin, in most of the practical applications, for instance in bike engines, or let's say in car engines, or let's say in any like heat transfer devices where they basically use fins to enhance the heat transfer, people do not use just one fin. Rather, what they do is they stack fins together. Okay, this is done such that the rate of heat transfer increases much more. Okay, so what they do is they stack fins together and then they look into something which is known as the overall surface efficiency. So for instance, the overall surface efficiency for, let's say, a stack of three fins like this. So for instance, this is one fin, this is one fin, this is one fin, and then they have an air gap in between these fins. The thickness of the fin will consider it as T, and the temperature of the base that is exposed, we will consider it as TB. Okay, and then what people do is they define this overall efficiency as eta O as the rate of heat transfer that would take place. Okay, so basically, so I'll tell you what is QT, but I'll first write this. So eta O is QT divided by Q max. Okay, it is just like the efficiency, rather some terminologies basically change. Okay, so for instance, if it was a single fin, we would have said that it is the rate of heat transfer from one single fin to the maximum rate of heat transfer from the fin. Rather, in case of overall surface efficiency, we tell that eta O is basically the total rate of heat transfer to the maximum rate of heat transfer. Where this QT, as I wrote here, this QT is basically the total heat rate from the surface area AT, where this AT, that the surface area we are considering, this consists of both the fin areas, both the fin areas and the exposed portion. So I hope you are clear, or at least I'm making sense with what I'm trying to say, and the exposed portion. Okay. All right. So what this QT means is, so what this QT essentially mean is, it is the total heat rate from the surface area AT, where this AT comprises of this exposed portion, which is basically this, plus the fin portion, which is basically this portion. Okay, so it's the total surface area that is being responsible for, transferring the heat. It consists of the exposed portion, which is basically this, okay, which bears a temperature of TB, and the fin areas also. This this culminated area is termed as the total area, okay, and the heat transfer that is associated from this total area, we will tell it as QT. Okay, similarly, this Q max, this Q max, okay, this Q max is the maximum heat transfer that can take place from this total area, just like the one that we calculated for a single fin. Okay, so this Q max would be mathematically equal to then H times AT times theta B, because this makes sense, right? Because as I said, that for a single fin, this becomes H times area of the fin times theta B. Now what we are saying is that we are trying to establish the maximum heat transfer from the total area, and that's why it becomes H times AT times theta B. But remember, this AT that we are writing here, it consists of both the fin areas and the exposed areas that are basically here. Okay. All right. So this means that I now can write this overall efficiency eta O as QT by H80 theta B. Okay. Now our task is to determine this QT. Okay. So the task for us is to determine this QT, and if we know QT, I can simply write this eta naught as this QT divided by H80 times theta B. Okay. So the next task, I mean the only task. So the task is to evaluate, okay, QT. All right. So by the way, if I if I tell you that I have n fins, okay, I have n number of fins here. So here I am saying it's 3, but in general I can say that I have n number of fins, and the area of each fin is AF, and the exposed area, that is this area, basically this and this, the exposed area, I'll write it as AB. Okay, if this is given to you, if this is basically given to you, can you tell me what is AT? This is easy, right? Just think about it, and can you tell me what is AT? If I have n number of fins, each of area AF, and the exposed area is AB, can you tell me what is AT then? Remember, AT is the total area which encompasses the surface areas of all the fins plus the exposed area. Where I repeat, this AB is basically all these exposed areas that do not have the fin attached to them. Can you tell me what is AT then from the geometry? So it's simple, right? It just becomes n times. Yes, exactly. You correct. I mean, you kind of correctly said, but it won't be n times AF plus AB. It would be n times AF plus AB, because I mean your thinking is correct, but maybe I mean when I was explaining, I was not clear. So the fact is that I'm telling AB to be all these areas and not just one area. Okay, this means this area, and all these areas. For instance, this 1, 2, 3, and 4. All these areas would contribute to your base area. Okay, and that is why it will be n times AF plus AB. So are you clear? Are you clear, Sandvi, why it is not NAB and just AB? Okay, yes. All right, thank you. Okay, so this means we have simplified one more step, that I have now figured out what is my total area. Okay, right. All right. So if I now have figured out what is my total area, can you now tell me what is this QT then? So QT, I will tell you that what is QT. As I have said, this QT is the total rate of heat transfer from this total area, which means this QT will have rate of heat transfer from n fins. If you have 3 fin, this would be three number of fin. If you have 4 fins, it would be 4 fins. In general, if you have n fin, it would be n fins. Okay. Plus, since it's the total area, it will also take care of the rate of heat transfer from the exposed area. Okay. So then, can you tell me mathematically what will be QT then? This is something that I wrote. Like, so this is so you just need to translate what I wrote here mathematically. Can you tell me? So this is easy, right? Because QT, so if I want to write the rate of heat transfer from n fins, I can write this as efficiency of a single fin. I will write it as eta f times the maximum rate of heat transfer from at n fins. Because this comes from the definition of efficiency of individual fins, right? So I can write the rate of heat transfer from n fins as the efficiency of a single fin multiplied by the maximum rate of heat transfer that would take place from these fins. The maximum rate of heat transfer, recall that it takes place when the entire fin is at the base temperature, which means it would be eta f times n, that is the number of fins, times h area of fin times theta b. Okay, this is equal to the rate of heat transfer from n fins. I repeat, why is that the case? Because that is typically because I can write the efficiency of a single fin as q fin by q max fin. Okay, and then I can write that q fin to be equal to eta times q max fin, and this is for one fin. And this term that you see here, this eta times this term, okay, this is basically nothing but the term that I have written here. And since there are n fin, I am just multiplying with n. Okay, I hope this is clear. Like, we are going very slow, but I hope this is clear. Why we have written is eta f times n h multiplied by af into theta b. Okay, plus this is for the fin part, right? We also need to consider the rate of heat transfer from the exposed area. The rate of heat transfer from the exposed area is easy, right? It is basically the heat transfer coefficient times the area of the exposed area AB multiplied by theta B, right? So this is basically your total heat transfer that would take place from the area AT. Okay, I hope this is clear. So if this is clear, then I think we are good to go. So what we need is, we just need to substitute this QT into this expression of eta naught to get the overall surface efficiency. Okay, so this eta naught is basically now written as eta f times of n, which signifies the number of fin multiplied by the heat transfer coefficient, times af times theta b plus h ab theta b divided by the maximum heat transfer was h at theta b, which means I will kind of have what? I will have theta b's being cancelled, okay, and h also will be cancelled, okay, which means I can write this eta naught, which is the overall efficiency of a stack of fins, as what can I write? So eta naught is basically eta f, okay, times n af plus ab by at. Okay, so I hope this is clear. Now I can do one simple simplification. What I can do is, can you tell me that can I write this AB as the total area minus n times AF? Can I do this? Can you give me an yes or a no for this? Can I write the exposed area as the total area minus the fin area? Yes, right? Of course I can do that. This means that your eta naught can be written as eta f times n into AF plus this is AT minus N times AF divided by AT. Okay. So if you simplify this, you'll end up getting a very nice expression which comes out as 1 minus, if you simplify, it becomes N times AF by AT into 1 minus of eta F. So this is an expression which gives you the overall efficiency of a stack of fins having n number of fins, okay, having the fin area AF and the total area AT, and the individual efficiency of each fin is eta F. Okay, so this is the expression. Okay, this is the expression for your overall fin efficiency. Okay, I hope this is clear. I want you to be clear from this step why how so basically how did I write this step from this step? Basically, how did I write the rate of heat transfer from n fins as the efficiency times the maximum rate of heat transfer from an individual fins multiplied by the number of fins. So are you clear? How did you do this? Can you give it to the yes or no? Because this step is important. Rest, like it's straightforward. Did you understand why did I write this? Uh, yes, okay, very nice. All right. So this, so the goal was, if you remember, the objective was to analyze a stack of fins instead of just analyzing one fin. Okay. So now the good, I mean, why, so what did we gain from this exercise? See, the thing is that if I now know, see, these areas are known to us, right? If I pick a single fin, I know its area, right? So AF is known, and the number of fins, of course, we can decide. And AT also, we can like decide, I mean, we can evaluate on our own because we have seen that AT is nothing but N times AF plus AB. Okay, this means that if I know the efficiency of a single fin, okay, then I can calculate the overall efficiency. That if I now use multiple fins, what would be this overall efficiency? And in a way, this will enable us to calculate the overall heat transfer that will basically take place from the surface from which we are trying to basically dissipate the heat. Okay, so this enables us to actually like study system of fins that are stacked together rather than so it enables us to study the system of fins that are stacked together in terms of the efficiency of a single fin. So by this, you understand, right? So by this, I don't need to individually do the analysis for one fin for each of the fins individually. Rather, what we will do is we'll just pick one fin and then do the analysis for one fin, calculate the efficiency of one fin, and then you will just multiply it with the number of fins that we have. Use this relation to get the overall surface efficiency for the fin structure. Okay, so that's the reason why we kind of use this term, which is known as the overall surface efficiency. So this is much more like, this is much more used in practical cases. As I have said, for instance, we don't just use a single fin, we use multiple fins that are stacked together. The benefit is again the fact that the perimeter to the surface area basically increases, which again enhances the rate of heat transfer. See, it's very clear. If I just don't use these three like fins together, and what I now do is I use the single fin, which maybe kind of like this. I use the single fin, okay. I mean, I can use a single solid fin, like, or what I was trying to say is that if I don't use this system and now I just used a solid fin, maybe like this, okay, maybe kind of like this, okay, meaning that this is now filled. Then you can establish that the rate of heat transfer from this solid fin would be much less than the rate of heat transfer from this fin structure, that using individual fins giving air gaps in between them. Again, the sole reason is that the perimeter to surface area ratio increases, which means we can now enhance the rate of heat transfer for the same surface area from which it is basically trying to dissipate heat. This is typically the reason why people use multiple fins rather than using a single fin. Okay, I hope this is clear. And yeah, so this is something that I want to discuss today. And I think now you will be in a good position to basically, sorry. So you will be in a good position to basically answer the questions from the assignment. I would suggest go through the like lecture series once, and then I think you can do all the questions of assignment 5. All right, so this is something that I wish to discuss today. We'll not discuss, so there are one numerical, but we will not do this numerical today. Maybe in the next class we will do the we'll go through this numerical. I repeat once again so the thing is that the session on 24th, we are supposed to have this session on 24th, but it is now preponed to today, so we'll not have the session on 24th. In the same in the same spirit, the session on 31st August only, that is the session on 31st August is postponed to 8th September. So we'll not have session on 31st August. Rather, we'll have the session on 31st August on 8th September. But remaining all other Saturdays, we'll have the session. For instance, we will meet. So we'll have the session on 7th September. Okay, we'll have a session on 7th September. We'll also have a session on 8th September. The 7th September is the usual session that we have. 8th September is the postponed session that we are supposed to have on 31st. Okay. So now we'll directly meet on 7th September, and we'll also have a session on 8th that I have just now said. So this readjustment is basically for the sessions on 24th and 31st, and for all other Saturdays we will have the usual 3 to 5 like classes. Okay. Anyways, you will be posted like before every session. You guys receive an email, and you will be posted like on that. Okay. And also like I'll also post it in the discussion forum. But we will now meet in the so the next class will be on 7th September. We will not have classes on 24th and 31st. Okay, so we'll meet on 7th September, and also we'll meet on 8th September. 7th and 8th we'll have continuous classes. That I have said the reason why. But yeah, the next class will meet on 7th. Uh, Actually, I'll not be in India. I'll go outside for a conference, so that's why these readjustments need to be done. Uh, but yeah, so that's the case. I apologize, like if you, I apologize for like if it created some inconveniences at your end, but this needs to be done. So yeah, so we'll meet. So if you have questions, of course you can ask today. But in general, we'll meet now on 7th September directly, which is a Saturday. We'll meet on 7th, and we'll follow the usual class timing from 3 to 5. Okay. Uh, I thank you all once again for joining. If you have questions, you can ask me. I thank once again for participating in this live session. So anyway, like you can watch this live session in the recorded form because it's always shared, but it's always good to join the live session because in that way I can understand like where you are basically trying to understand things, where you are basically getting stuck, and that it's a good way of like learning together, and then like understanding the points which need to be clarified. Which needs to be clear because see, the lecture series are also being recorded, right? So there is no point you are watching a lecture series that is being recorded and then you are also watching the recording of the live session. It doesn't, I mean, to me it doesn't make much of a difference there. But of course, like if you have difficulties and if you have prior commitments, then of course you need to watch, and that's why we have the recordings. But like if you have your chance, try to attend the lecture try to attend the live session. I thank Sanvi, like as Sanvi is present here, I thank Sanvi for like attending this session. If you have any questions, you can ask. And if you have any question at the later stages also, please feel free to like post it in the discussion forum. And I hope you guys enjoyed this class today. I hope you have appreciated the use of extended surfaces. In the next time, that is on the next time we meet, we will be discussing something which is known as transient and 2D heat transfer in conduction. There is something which is known as lump capacity analysis, or it's we will see what all those things means. But yeah, they are also like interesting in their own way. But yeah, that's it. So if you have any questions, you can ask. Yeah, thank you, sir, for explaining. So yeah, thank you. Yeah, thank you, Sanvi. Thank you, like for appreciating. Thank you very much. And if you have any questions, you can ask, or we'll call it a day. Yeah. Okay. So thank you, guys. If you have any questions, you can again post it in the discussion forum. If you have any questions throughout any time, like we'll be happy to address it like individually. Thank you very much. I'm calling off this meeting. Thank you for joining the session. Goodbye.